In this video, we'll be looking at subunit 4.3, production of some important metals and nonmetals. This video is part 2 of subunit 4.3 and we'll be focusing on important nonmetals. By the end of this video, you should be able to outline the production of nitrogen and discuss its chemical properties. We will also discuss the production of phosphorus and its chemical properties, as well as oxygen and its chemical properties. From there, we'll move on to the production of sulfur and describe the main chemical properties of sulfur. Finally, we'll outline the production of chlorine and describe its main chemical properties. So to begin, we'll start with nitrogen. Nitrogen occurs in nature as in its elemental form as a diatomic molecule, N2. N2 exists in atmospheric air and constitutes about 80% by volume. In addition to its elemental form, nitrogen can also exist in the form of compounds, such as sodium nitrate, also known as Chile saltpeter, and potassium nitrate, which is known as just saltpeter. It is also found in DNA molecules in the proteins of all living things. In order to produce elemental nitrogen at an industrial scale, we must remove impurities from air. In order to do this, compressed air is put under high pressure at low temperature. This removes carbon dioxide and water vapor. As the temperature continues to decrease, the air condenses to give a pale blue liquid. Using fractional distillation, nitrogen is collected and stored in steel cylinders under pressure. Argon distills off the mixture at -186 degrees Celsius, leaving behind a blue liquid of oxygen that boils at 183 degrees Celsius. So looking at the schematic, we can see that using the distilling column, we are able to fractionate liquid oxygen from argon gas and nitrogen gas, and can therefore separate these three elements. In the laboratory, nitrogen is prepared using a different method. In this process, nitrogen is prepared by warming an aqueous solution containing ammonium chloride and sodium nitrite. Through this reaction, we're able to generate nitrogen gas. Nitrogen gas is colorless, odorless, and tasteless. It is inert, and that is why it's found in atmospheric air as N2. The inertness of nitrogen at low temperatures is due to the strength of the triple bond between atoms. Nitrogen reacts with group 1A and 2A on the periodic table to form nitrides, and examples of these reactions can be seen here. It can also combine with oxygen at high temperatures or in an electric arc to form oxides, as seen in these examples. Nitric oxide or nitrogen monoxide is a colorless and reactive gas. In the presence of oxygen, it forms nitrogen dioxide, a reddish-brown gas. The reddish-brown gas can dimerize at low temperatures to give the colorless gas of dinitrogen tetraoxide. So overall, nitrogen can form many different types of oxides, including dinitrogen monoxide, otherwise known as laughing gas, dinitrogen trioxide, dinitrogen pentoxide, and can also react with hydrogen in the Haber process to form ammonia. The ammonia derived from this process is used to manufacture fertilizers and for the production of nitric acid. Nitrogen is used in a number of applications. One way that we're able to see nitrogen in everyday processes is in food packaging to prevent oxidation. It is also used to create an inert atmosphere in the production of semiconductors. Liquid nitrogen is used as a refrigerant to preserve bull semen and blood. And nitrogen's major use is in the production of ammonia. Now we'll move on to talk about phosphorus. Phosphorus is an abundant element ranked 12th in abundance in the Earth's crust. It exists naturally only in compound form. Examples of these compounds include rock phosphate, fluoroapatite, and it is also found in teeth, bones, and DNA. One unique property of phosphorus is that it exists as allotropes. Allotropes are different forms of the same element with the same physical state, but with different physical properties. The two common allotropic forms of phosphorus are white phosphorus and red phosphorus. White phosphorus is very poisonous. It is a white, waxy-looking substance. It melts at 44.1 degrees Celsius and boils at 287 degrees Celsius with a density of 1.8 grams per centimeter cubed. It consists of individual tetraatomic molecules and is an unstable form of phosphorus. Red phosphorus is prepared by heating white phosphorus in sunlight for several days. Red phosphorus's density is 2.16 grams per centimeter cubed, and it is far less reactive than white phosphorus at normal temperature. It consists of P4 molecules linked together to form a polymer, and this is what makes it more stable. In order to industrially produce white phosphorus, a mixture of crushed rock phosphate, silica, and coke are heated in an electric furnace. The vaporized phosphorus is condensed and collected and stored underwater because, it is highly reactive. White phosphorus is stored underwater because it spontaneously ignites in the presence of oxygen. So in summary, phosphorus can occur as a white, waxy solid, a brownish red powder, or a black solid. Its boiling point is 280 degrees Celsius, and its melting point is 44.3 degrees Celsius. Its density in the form of white phosphorus is 1.82 grams per centimeter cubed. Phosphorus will react with oxygen in a limited oxygen environment and also in an excess oxygen environment. Both of these oxides will dissolve in water to produce acids. Phosphorus reacts with limited or excess chlorine as well. We will now move on to discuss oxygen. Oxygen is the most abundant element on Earth. It's found in its elemental state in atmospheric air and comprises 20% of the atmosphere by volume. It is also found in compound forms such as oxides, silicates, carbonates, and phosphates. In order to manufacture oxygen, it is manufactured industrially by the fractional distillation of liquid air. Oxygen is a highly reactive element and will combine directly with most elements to form oxides. It combines with metals to form metal oxides, also known as basic oxides, as we reviewed in Unit 2. And will also combine with nonmetals to form acidic oxides. Oxygen also supports combustion and is useful for the burning of charcoal and hydrocarbon fuel. Oxygen is used in a wide number of industries, including paper manufacturing, ceramic creation, glass making, and it is also used in petroleum processing, pharmaceuticals, metal refining, medicine, high-altitude flying, deep-sea diving, as well as industrial uses with combination with acetylene, propane, hydrogen, and other fuel gases for metal cutting, welding, and hardening. Now we will talk about sulfur. Sulfur is found in the form of compounds such as galena, pyrites, cinnabar, sphalerite, gypsum, barite, and hydrogen sulfide. Sulfur is extracted from underground deposits using the Frasch process. 3 concentric pipes are sent down to the sulfur deposit. Superheated water is pumped through the outermost pipe, and hot air is compressed in the innermost tube. Sulfur, air, and water come to the surface forced by the hot compressed air in the middle tube. From there, the molten sulfur is then cooled and solidified. Sulfur is used in a number of applications, including the vulcanization of black rubber, fungicide, black gunpowder, and also for the production of sulfuric acid. Sulfur will react with metals when heated to form sulfides. It will also burn in oxygen to form oxides. Sulfur is also the raw material for the production of sulfuric acid by the contact process. During the contact process, sulfur is first oxidized using oxygen gas to form sulfur dioxide. The sulfur dioxide is then converted into sulfur trioxide at high temperatures and in the presence of a catalyst. Sulfur trioxide is then absorbed into concentrated sulfuric acid to produce oleum. The oleum is then added to water to produce the desired concentration of sulfuric acid. Finally, we'll talk about chlorine. Chlorine is found in group 7A, the halogens, on the periodic table. It is the most abundant element among all halogens. It is normally found in compounds in the form of chlorides with either sodium, potassium, calcium, or magnesium. Sodium chloride or table salt is the chief source of chlorine. It can be obtained from seawater or as deposits of rock salt. Chlorine is manufactured by the electrolysis of concentrated aqueous solution of sodium chloride or brine. As we saw before in Unit 3, we are able to produce chlorine through the electrolysis of concentrated brine. Chlorine is formed in the anode and the reduction of water occurs at the cathode, producing hydrogen gas and hydroxide ions. The electrode and the overall cell reactions are oxidation of chlorine to chlorine gas at the anode and reduction at the cathode. Chlorine has a greenish-yellow color and is usually found as a gas. Its melting point is negative 102 degrees Celsius, and its boiling point is negative 34 degrees Celsius. It is soluble in water and is extremely poisonous, causing inflammation of lungs and mucous membranes if inhaled. Chlorine will react with heated metals to form chloride salts, and examples of these reactions can be seen here. It will also react with hydrogen in the presence of charcoal as a catalyst, forming hydrochloric acid. Chlorine will also displace less reactive halogens such as bromine and iodine from aqueous solutions of their compounds. When dissolved in water, chlorine will react with it, forming an acidic solution containing hydrochloric acid and hypochlorous acid. This type of reaction is called a disproportionation reaction, where chlorine itself is reduced and oxidized. In its everyday applications, chlorine is used as a bleaching agent and disinfectant, and to keep drinking water and swimming pools safe. It also is used to oxidize dyes and to bleach colored materials, and to remove yellow or brown colors from wood pulp, paper, and cotton. In summary, nitrogen composes about 80% by volume of the Earth's atmosphere, and it is manufactured by the fractional distillation of liquefied air. Overall, nitrogen is relatively inert. However, its reactivity increases when heated and combined with metals of group 1A and 2A to form nitrides, or with oxygen to form oxides like nitrogen monoxide and nitrogen dioxide. Phosphorus is manufactured by heating mixtures of rock phosphate, coke, a carbon source, and silica in an electric furnace. It has two common allotropes, white and red phosphorus, with white phosphorus being highly reactive and red phosphorus being relatively stable. Because of its reactivity, white phosphorus must be stored underwater. Finally, phosphorus will react with oxygen and chlorine. Oxygen makes up 20% by volume of the air and is manufactured by the fractional distillation of liquid air. Oxygen overall is the most abundant element in the Earth's crust. Sulfur exists in its elemental state in underground deposits from which it is extracted using the Frasch process. Sulfur reacts with oxygen to form sulfur dioxide and sulfur trioxide, and it is also used for the manufacture of sulfuric acid by the contact process. Chlorine is manufactured by electrolysis of brine. It is a powerful oxidizing agent and reacts with heated metals to form chlorides. Chlorine and chlorine water are used to bleach colored materials and also used as a disinfectant. Review question 1. What are the main natural sources of nitrogen, phosphorus, oxygen, sulfur, and chlorine? Nitrogen and oxygen are found in the air, while phosphorus is found in rock phosphate. Sulfur can be obtained from underground deposits, while chlorine is found in brine. Review question 2. Describe the main processes involved in the production or extraction of nitrogen, phosphorus, oxygen, sulfur, and chlorine. Nitrogen and oxygen are obtained through the fractional distillation of air, while phosphorus is obtained through heating rock phosphate in an electric furnace. Sulfur is extracted using the Frasch process, and chlorine is obtained using electrolysis of brine. Question 3. How do nitrogen, phosphorus, and sulfur behave when heated in air? Sulfur, nitrogen, and phosphorus will form oxides when heated in air. Question 4. Write an equation for the reaction of chlorine with water. Chlorine is both oxidized and reduced in water to form hydrochloric acid and hypochloric acid. Question 5. Consult the books present in your library and describe with the aid of labeled diagrams the laboratory preparation of the following molecules: A, nitrogen, and B, chlorine.
In the laboratory, nitrogen is prepared by heating a mixture of ammonium chloride, sodium nitrite, and a small quantity of water. The presence of water prevents ammonium chloride from subliming when heated. Initially, the two substances undergo double decomposition to form sodium chloride and ammonium nitrite. The ammonium nitrite formed here then decomposes to form nitrogen gas and water vapor. Nitrogen gas is collected by downward displacement of water. But what will happen if ammonium nitrite is heated by itself? If this happens, then the ammonium nitrate decomposes to produce nitrogen gas. However, this reaction is very fast and may prove to be explosive.
Tripod stand, burner, round bottom flask fixed to a clamp, thistle funnel, delivery tubes and gas jar. Chemicals required: potassium permanganate, water, concentrated sulfuric acid, concentrated hydrochloric acid. Arrange the apparatus as shown. Add a few drops of concentrated hydrochloric acid to the potassium permanganate solution through the thistle funnel. Observe the reactions that take place. 2KMnO4 plus 16HCl gives 2KCl plus 2MnCl2 plus 8H2O plus 5Cl2. Chlorine is collected by the upward displacement of air as it is heavier than air.